not going well today. Wow. Hi from Westmont. We're broadcasting live, but we're broadcasting the wrong thing. Go. That would be the right thing. That's good. Great. I'm on the screen. You've got audio. Big face is there. No, my face isn't there. No, my face is there. All right. Wow. All right. Welcome to Westmont College Mayterm. It's live from Santa Barbara and all the fun that comes with being live. We're in Winter Hall, room 110. This is our seminar, part of a 5-week class. And today's lecture is scheduled for 2 hours. It's going to be a little bit less because we had a little bit of technical trouble this morning. YouTube wasn't doing everything that we were told YouTube would do for us. So I had to fix it on the fly. So for those of you who are following along at home, you are not actually going to be live on this second. So maybe, yeah, put a Great. For those of us who are following along in real time, we're on Slack and hashtag broadcast questions. We're monitoring that as we chat. Got a guest in our audience today, in our live studio audience this morning. So welcome. And all right, today of all days, it's good to take a moment, just arrive and start this thing off right. Make sure our notifications are off and any other notifications that we don't want present. To get rid of them. Wow, with everything going on and all the notifications and phone calls that I get, I always have to sort of just take a second and breathe when these classes start. Make sure that we're ready to go. One of the things that we've been doing at the beginning of each of these classes is talking a little bit about the ethics around computing. And one of the things we run into a lot in computing is the way in which computational systems end up interacting with legal requirements in various ways. And this is interesting to me because it feels like a lot of Jesus' teaching have to do with the law and ways in which legal requirements at the time, mostly he was concerned about religious laws at the time, interacted with what he intended for what his teaching was. And broadly over the arc of the Bible teaches that the law is present to show us that the problem isn't with regulation, but it's with our hearts. Nevertheless, as technologists, we end up in situations where we confront the law a lot because we're finding ways, we're in a new forefront of our society, and laws are often slow to catch up. I can't post it. Okay, we'll do it later. That's okay. So we've seen some examples of legal limits versus what is right or what is holy or what is Christ honoring. We've seen examples of legal regulations that fall short, places where Christ calls us to a higher standard. A lot of examples of this in the Sermon on the Mount. And as technologists, we will find ourselves in positions where we have access to information and systems that we didn't have to break any laws to get access to, but all of a sudden we find ourselves with a certain amount of power that we could abuse and nothing preventing us from doing that. So that would be an example of maybe some place where we've got to find a different moral authority other than the law in order to do what is right. But we also have examples of legal restrictions that are too strict. And in this case, Christ calls us to a deeper understanding of freedom most of the time. And his example was an example of picking grain on the Sabbath. For the religious law at the time, that was a violation of the law of the Sabbath. And Christ came back and said, no, that's not what the Sabbath is for. In a technological sense, we can find ourselves in some situations where legal restrictions are too onerous as well. And I would say an example of that would be the DMCA, the Digital Millennium Copyright Act. Violating those regulations, however, does bring you into conflict with the state, and you are liable for penalties as a result. So even though those regulations may be too strict, you should be very, very careful about the circumstances and situations in which you go about breaking them, because you are, in fact, breaking the law in that case. There are also examples of things where there are legal regulations that actually permit things which are wrong. And so an example of that historically in the U.S. would be slavery. There was a time when slavery was legal. That is not okay. And so In those cases, Christ calls us to resist them, to change them, or to redeem them, redeem the law, or the effects of the law. And so, in a technological sense, this could be a lot of different things that are permitted, which are wrong. And I would put out there that pornography is probably one of them. Largely delivered through a technological medium these days, that's something which is totally permitted under, freedom of speech. Regardless of what the law should be, that's certainly something permitted, which just goes against the teaching of Jesus in as far as adultery goes. It also changes our relationship with other people in ways that are really unhealthy. Just one example of where technology enables that, though. There are a lot of other examples of legal regulations that permit things which would be wrong. There's a robust discussion that you could have about whether a legal restriction should be put in place even though something is wrong. Issues of freedom and issues of conscience sometimes cause us to want to allow people to do some things which other people think are wrong in the name of maybe humility, maybe not necessarily always knowing what is right, being convinced that something is right for ourselves, but not being sure that that is something that we should say is legal for everyone. It's a hard conversation to have, but as technologists, we run into it all the time. And so it's one of those things that we have to be cognizant of as we're doing our work. That's all I want to say about that today, actually. I had an example of something else that we could talk about, maybe I'll bring that up tomorrow. So I'm going to skip over that slide real quick. So regarding what we're doing here today, we are working through we finished up chapter 5 last time, or we started on chapter 5. We're actually going to continue a little bit on chapter 5, changing the schedule a little bit. We have a quiz for chapter 3 due on Friday, a programming assignment for chapter 3 also due on Friday. Quiz for chapter 5 next Monday, and we're shifting a little bit. We're kind of blurring chapter 5 and chapter 6 today, and hopefully going to get to chapter 15 by the end of the week as well. So last time we looked at JUnit test cases. We looked at that in detail. We looked at the Java FX framework. We had an opportunity to put together a user interface that was a desktop interface that pops up an application window and that we could code with. For those of you who weren't here in class and weren't able to share the code, I don't remember if we shared that. Did we share that on Source? Okay. Let me see how it goes today in terms of sharing it. But regardless of whether I share it today, I put an archive of that project on Canvas. So if you go to what are we on today? Day 8. So if you go to day 7, there should be a file there, which is a zip file. And if you download that file, you can import it into Eclipse through their import functionality, and it's the equivalent of if we shared it over Saros. I don't think we're going to have a chance to do that today, but I can certainly do it after class if we need to do it. We also talked about decisions and if-else statements and if statements, and what I would like to do today is exercise some of those things that we learned and introduce a few new ideas around it before we get into talking about loops. Okay, so if statements. Last time we had this structure of an if statement. We knew that there was reserved words if and else, and we introduced this little bit of code that was part of our Java FX application that helped us to create a little utility that would determine whether someone passed a class or not by having them enter in a grade and then evaluating whether or not that grade was greater than or equal to 60. And you can see in the code on the left, it's just a snippet of the code, we would check to see whether the grade is greater than or equal to 60 by using the greater than or equal relational operator. And if it is, we would enter into this block of code that starts with that comment pass there. Actually, I can sort of highlight it. That starts with that pass comment up here. And then if we passed, then the message would be stored, you passed. And we would do some work with our user interface where we would set our text to be that message, and then set the styling in such a way that it would also reflect the fact that it was sort of green, like as if we passed. So that's one block there. And then if the grade was less than 60, strictly speaking, we would fail, and we would drop into this block over here, where we would store the message you failed, and then we would set the text to the particular message and set the color to a more red color to give us a visual indication that something went wrong. So when I introduced the idea of the if-else statement, I introduced this idea of a flowchart. Sometimes people have a hard time seeing the connection between how the flowchart works and how the code works. And so I went ahead and explicitly took the flowchart model and took that code and then put the flow chart over here on the right side. And you can see that in the flow chart, if we drew it in a flow chart model, you can see that that diamond shape represents the question that we're asking or the relational operator that we're invoking. In this case, is grade greater than or equal to 60? I left the parentheses around it because Java requires parentheses. Other languages don't require parentheses in if statements, but Java does, so I left it there. And based on whether I should have annotated. I didn't annotate on the slide, sorry. Which was the correct, sorry. I didn't annotate which was true and which was not true. So let me just do that right here. So if that evaluated to true, we would go to the right branch. And if that evaluated to false, we would go to the left branch there. And you can see that those two blocks of code get run, and you can see that there are multiple lines in each one of those blocks. Those curly brackets are scoping out or giving us a boundary for what code is in each bracket. And you can also see that after those two bits of code get run, they get rejoined down at the bottom as we finish that if-else statement. And sometimes it's easier to see in this flowchart model how those two blocks of code are never both going to get run. In order to get from the top of that diagram to the bottom, you're going to have to either go the left route or the right route based on the result of the grade. So that's just an important understanding of how the logic for an if statement runs. Now, if we hadn't put an else statement in place, if we only had a true block in place, then this would go away, and our line would just go directly through here, such that we would only have one block of code that's written if it's true, and we wouldn't have a block of code written if it's false. Okay? So that would be one kind of way which we could alter it. The other thing that we could do is we could have put a nested if statement in, and we could have had another little diamond in here that had another set of code within it. And that would have been equivalent to what it would be like if we had put an if statement within one of those curly brackets. So this is the false branch. So if we had put another if statement in there, then we would have had a nested if loop. And so there are a lot of different ways in which you can change the architecture of this if-else statement to achieve the kind of decision-making that you're interested in actually achieving. Just to be clear about what the different relational operators are that we can use, I just want to take a second to lay them out. They're a little bit different than math symbols because we don't have access to the full range of math symbols in the Java language. We have to use 2 symbols for some of them. So we have 6 different relational operators that we can use within the body. Actually, it's not exhaustive. There are some other ones. But within the body of our if statement, the ones that we commonly see are listed here. And I'll read them down from the top using just the semantic understanding of them. So the first one is greater than, so it's true if the thing on the left is greater than the thing on the right. The next one's greater than or equal to, and so that's slightly different than the one on the top because it will be true if it's greater than or equal. The top one is strictly true only if it's greater than. We have the opposite sentiment in the third and fourth one if the left is less than the right or less than or equal to the right. That's those two guys down the next two. Then we have this one, which is a double equals. The double equals is an interesting one, because it is useful for testing whether two things are equivalent, but actually it's not the best way. Well, you can use it on objects, but it's probably not going to do what you think it's going to do on objects. And so we need to talk about that because it's a little bit different than just testing whether two things are equal. And then the not equals is the flip sign of the equivalency there. Any questions about those, notwithstanding the mystery around the double equals? Okay, so let's take a second and see if we can convert the following elements to code. So what I'd like you to do is just write an if statement that, if true, will meet the requirements of the English phrase on the left. Okay, does that make sense? So each one of these could be written as an if statement with a body, but I'm just interested in what the relational operator would be for those 5 elements. So what we'll do is we will take just 5 minutes, and if you guys want to jot it down in code, but for 5 minutes we'll go offline so that people can work on this, and then we will come back at 56 in order to talk about what answers people came up with. Okay, we're back online, and our goal was trying to take these different statements and convert them into relational expressions that we could put into an if statement. And some of them are a little tricky, so we'll just go through the room here and see what we came up with. Joy, do you want to start us off with one that's maybe trickier than the others? What did you get for n is at least 10? Okay, so if n is 11, that will be true, and 11 is at least 10. All right, what if is 10? Should 10 be included? Probably greater than or equals, I'd say, yeah. Greater than or equals 10. That one's a little tricky because the translation from the English phrase to the relational operator isn't direct. So you have to kind of think through it. And I don't know if you noticed what I just did there, but I kind of ran tests in my head automatically. Like, what if it's 0? What if it's 10? What if it's 11? Would that match the English phrase? All right. Let's see. Next one. Lisa, what'd you get for n is negative? Great. Anyone get a different way of doing it? Okay. Tim, n is 0.
If bracket n equals 0 bracket.
Okay, that's pretty good. Sorry, got my second grade handwriting on my slide here. So that's the basic idea. That looks pretty good. All right, Boaz, what'd you get for not 0?
It should be n exclamation point equals 0.
Great. So that's an exercise mostly in just knowing what the syntax is for not equals. Different languages actually can have different symbols for not equals, so that's good. And then we're wrapping around again. Joy, n is hello, or s is hello. Okay, so if s is a string, that's going to work out okay. This is a trick question, though, because it's not really the preferred way of doing equality on objects. We have another way of doing equality on objects that's a more robust way of doing it that we haven't introduced yet. So that question is mostly just a trap. It's a trap. And so in the case of strings, that's going to work because of an exception in the way that strings are handled. But we're going to look at a better way to do it with strings with objects generally in a second. Before we get there, let's try one more. Let's try doing what's the opposite of these statements. So try and work through what you would get if you wanted to do if and the opposite of it. So we'll take a second to do that. Let's see, maybe go a little bit faster. So we'll come back in 4 minutes at 03. Be right back. Okay, we're coming back, and we'll try this again. We'll go through the same order to give everyone a fighting chance here. So, Joy, what do you think the opposite of n is at least 10 is? Great. I think that's good. Everyone buy it?
No.
So here's the trick to this, though.
No, I don't buy it.
You don't buy it?
Yes. It has to be. Is at least 10 means it has to be greater than 9. Wait, no. No, that wouldn't even work. It has to be equal to or greater than 10.
But we're doing the opposite of it.
Yeah, so less than or equal to 10.
Less than 10.
Yeah.
Not less than
or equal to 10.
No, because n is at least 10 would be greater than or equal to 10. And so the opposite of that wouldn't include 10, so less than.
Yes.
So basically what Joy said.
Yes.
Right, okay, that's right. Which reminds me, I want to add to the broadcast. I want to add a laugh track. I want to be like, ah, or oh, a round of applause.
If you,
Right,
if
so-
you add that one, then we have to add the laugh technical difficulties one.
Yeah, okay, so tomorrow stand by for a really large audience of really enthusiastic participants. So here's the trick. There's actually something you could do here that sort of would make this really easy. If you remembered what you did from last time, you could actually just put a not in front of the whole thing. Oh, sorry, greater than or equal to 10. So that expression negates whatever is inside the parentheses. So you could do that, or what Joy said, which is n less than 10. Both of those expressions are the same thing. Okay, but going back to, let's see, Lisa, what's the opposite of n is negative? Greater than 0. Or, like we said before, well, I guess this is a little bit tricky, because the opposite, oh, greater than or equal, that's what you said, right?
I didn't, but yes, that is correct.
So the opposite of n is negative is not, well, I guess it turns a little bit on what you mean by the opposite. Because 0 is neither positive nor negative, if you interpret the opposite as n is positive, then you would have to be n is greater than 0. But if you interpret the negative as just not n is negative, then it would be n is greater than or equal to 0. So there's a little room for interpretation there. What you mean by the opposite. Do you mean everything that's not covered by that statement, or do you mean some kind of semantic opposite?
Semantic opposite.
So semantic opposite would be the top one. N is positive. But logical negation is the bottom one. Okay, wow, this is turning out to be more complicated than I expected. All right, Boaz, n is 0. The opposite of that is,
And it's not 0.
and how do you indicate that?
And exclamation point 0.
An exclamation mark equals.
Oh, yeah. That's nice. Almost forgot about it.
Okay, Lisa, n is not 0. The opposite of that is.
And
Oh, sorry, I skipped Joy. Good. All right. Oh, how did I do that? Did I add one more? Joy, S is hello. The trap. Great. So that would be the natural understanding. That's going to work with strings. The best way to do it, and the way that we're going to learn, is to do not s dot equals hello. Not equals s dot equals. All right. So that's messy. We'll look at it in a second. Okay, great. Thank you for playing along with me there.
instead of writing n equals 0, this might be more confusing, but could you also write exclamation point n does not equal 0?
Yep. Yep. That's
Like it does not equal.
yep. Not n not equal to 0 is the equivalent of n equals 0. Hmm? Yep. You could also just do this as well. You do not n not equal to 0. Yeah.
You can do multiple exclamation
Yeah, because they're applied and they just negate whatever's before it. Yeah. Okay, let's see. Got a bad slide in here. Let's skip over that one. All right, so something to be said here about comparing floating point numbers. I think we talked about this sort of ad hoc once earlier in this class, and I wanted to just make sure that we talked about it formally, that when we compare floating point numbers, we have to be really careful because of precision issues that are present in computing. If we want to compare whether two doubles are equals, you probably don't want to use the equals operator because exact equality is probably not what you're looking for. So if we take a look at this code here on our slide, you can see that we're creating two doubles, one which is named R and one which is created D. And R, we're calculating the square root of 2. So what's happening there? We're using the class capital M math. Square root is a static method, and so we're able to call that static method without instantiating a math object because it doesn't use any of the instance variables in math. So just like our main method is a static method, square root is also a static method. And what Eclipse will do, if you type that in, it will put it in italics to indicate to you that it's a static method. So you would expect that if you have R and you take the square root of 2 and you set R equal to the square root of 2, then when we calculate D and we say R times R, that should reconstitute the 2. If math is doing what we think it should be doing, the square root of 2 multiplied by itself should be 2 again. And so if we then subtract 2 from that product, we should end up with 0. But so now what we have is we have a double, D, and we're comparing it to 0 using exact equality. And what we find out is that that doesn't work. That doesn't end up being true. What we end up with is the result that's down there in the bottom outside the highlighted box where we print out that square root 2 squared minus 2 is not 0, but, and then this number, which is very small, 4.4 times 10 to the minus 16th, but still not 0. And the problem is because we can't represent some of these numbers exactly. Because of the way floating point is, we aren't able to get those numbers exactly. And so what happens is we end up in a situation where we don't actually want to compare exactly what's happening. So what's the response to that? The response is instead to see whether the difference between those two numbers is small enough. And we've seen that baked into the JUnit testing when we compare two doubles. We would want to instead do something along the lines of use the math ABS function. That's absolute value. And say R minus D. So that's going to calculate the difference between those two numbers. And that's going to be small, but it's always going to be positive. And then we're going to say if that's less than some constant that we care about, which will be epsilon, we say if that's true, then they're close enough. And that's the equivalent of equality. It's a little not perfect, but that's the way it works when we've got floating point numbers that are approximate. And so that just means that when you do these calculations, you have to be very specific about how close you need to be. And you also, you kind of just need to remember that because it's easy to write code where you're doing expressions that entail floating point arithmetic, and you just expect it to be equal to 0. And sometimes it'll work because it does end up being exact. You don't always lose precision, but sometimes you do. And so this is just something to be very, very cautious about whenever you find yourself doing evaluations of the results of computations. Okay. Does that make sense? This is something that catches people a lot. And I just want to make sure you're looking for it. All right. I guess another thing to point out is that if you're working with with floating point arithmetic and you're doing less thans or greater thans, you're in a lot better situation because it tends to be that greater thans and less thans work fine. It's just that equality that you're concerned about. And if you're doing a greater than or equal, you're also running into that situation as well. All right. So let's get back to that issue of comparing two objects. We said that a different way of comparing equality on objects is to use this equals method. And so this would be the best way of comparing two different objects to see whether or not they're equal. Any ideas why? What the difference is between doing string 1 dot equals versus string 2 equals? Or using the double equal sign versus the equals method?
I don't know. Does it approximate fit so it's not exact?
That would be a good guess. That's not what happened. That's not what's happening. That's a good guess.
Does it not take into account like capital or lowercase?
That's another good guess. What exactly do we mean by equals is sort of at play here, right? Does capitalization count? That's not what's happening, but that's a reasonable guess. So first, let me just make sure you understand the syntax. In this case, what we have is we have string 1. There's a method that's part of string 1 called equals. That method takes another string, and it returns true or false based on whether string 1 and string 2 are equals. And so equals itself is implemented as part of the class. Okay, so the problem here is, I think is kind of interesting in as much as we saw it in Python too, because we have this issue of what do we mean by things being equal. And again, if we kick out and we think about a legal system, and we think about whether two people are equal, we could say, are Tim and I equal? And the answer is, well, what do you mean? We're not the same person. So in that sense, we're not equal. But maybe in terms of the rights that we should have afforded to us, we are equal. Maybe if you're asking if we're the same gender or the same height, that we might be close enough to be considered equal in that regard. And so what this equals method enables us to do is to be very precise about what we mean by equality, equality under what standard. But what the double equals is testing is whether or not it's actually the exact same spot in memory or not. So whether two references are aliasing the same piece of memory. And so the double equals is almost like the strongest possible equals you could have. Not only are two objects equal, but they're actually the same object. You can imagine if we had two rectangle objects, and those two rectangle objects had instance variables, x, y, width, and height. They could be equivalent in that each of the instance variables would have the same value, but they would be different memory objects. So let's take a look at this. Let's kick into Eclipse and see if we can demonstrate this working. All right, so let me clear up my environment here. And let's go over to the rectangle class that we created earlier. And let's just remind ourselves what that looks like. So we have a rectangle class with x, y, width, and height. And we have the ability to construct it. And we have the ability to check the x with getters and setters for all these things. And we can check area, height, and perimeter. So maybe it would be helpful to write an equals method here so that we can be clear about what it is that we are we're checking. So let's actually, you know what? Eclipse does this for us. So let me show you how to do it automatically in Eclipse. So if you go under source and you come down here and you say generate a hash code in equals, I won't explain what the hash code is for now, but if you generate your own equals method, it'll say, well, what things have to be equal in order for these two classes to be considered equal? And we say, well, the height, the width, the x, and y all have to be equal in order for rectangles to be equal. You can imagine that what you care about for two rectangles to be equal is just the width and the height they're the same. You don't care about where they are, you just care about whether they're the same size. And so it's up to you to decide, well, do two rectangles have to be on the same location and be the same width and height to be equal, or do they just have to have the same width and height? So what do you think? What should we do? We can implement either one. Just the width and height. All right, one vote. First mover advantage. So we're going to write an equals method that says that two rectangles are equal if their width and height are the same, regardless of where they're positioned. Okay, great. It'll ask us where we want to put it. We'll put it at the end. We'll hit OK. And let's look at what got generated for us here. All right, so what did we get? We got this kind of complicated equals method, but basically we're going to get passed in this other object, which is going to be the other thing that we're comparing to. And first we're going to say, well, if the object that we're currently in and the one that was passed in are literally the same object, we're just going to really quickly return true, because we don't have to do anything. If they're the same memory, we're just going to return true. If the thing that was passed in is null, it's an error check, we're just going to return false automatically. Great. If the thing that was passed in is not the same class as what we are, so if someone's checking equality on something that's not a rectangle class, then we're just going to immediately return false as well. So this is a way of checking to see if we're comparing the same kinds of objects. And then what we're going to do here is we're going to cast the object that was passed in as a rectangle, because we're sure that it's a rectangle if we got past this line. So we're not going to get any errors here. And then we can do the checking in the middle. So now we say, well, if our height is not equal to null, and the other height is not equal to null, or sorry, if our height is equal to null and the other height is not equal to null, then that's false, because the heights are not equal. One is null. But if both of them are not null, then we can say if, however we consider doubles to be equal, If they're equal, then we'll return true in that case. Otherwise, we'll return false. And finally, we'll do the same thing with width. So Eclipse did this really nice thing for us where it's going to just write the code for checking equality along the way. So now let's see that getting demonstrated here. We'll, how should we do this? Let's make a, let's grab a main method. Let's just create a new class in which we'll do this. Let me share. Do you want me to share this with you guys as we go? You okay? Okay. All right. All right, and I'm just creating another class so that I can practice my spelling, so that I can create a main method so I can work with it. All right, so in my main method, what I'm going to do is I'm just going to create a new rectangle. We'll say A. That's going to be a new rectangle, and we'll put it at 0, 0, and we'll make its width 10 and its height 20. And we need to import that. And we need to spell it right. Did I spell it right? What's going on there? I think I must have spelled it wrong. Okay. I couldn't see the spelling. So we have one object, which is a rectangle A. We have another rectangle, which is B. And we will make its position different. We'll put it at 5, 5. But we'll keep its width and its height the same. And now we will make another rectangle. And we'll make that called C. That's going to be a reference to a rectangle, and we're going to make that point to the exact same memory location as the one that A points to. And so now we can say if A equals B, then we'll print out that fact. All right, so if we run this code, what we see is that A equals B is false. Does that make sense? We just created two rectangles that we said are going to have the same value. Well, they don't have the exact same number, so let's just prove this point here. Let's let me make a C. All right, so A and B are two rectangle objects. They have exactly the same instance variables, but if we check them with the double equal sign, they are not equals. You see the impact of that? Do you see how easy it would be to use double equals to check equality and get exactly the wrong answer? Because it seems like they should be equals. Be equal. Okay, well, that isn't the case, but if we examine A and D, change our output here. We run that now. We see that A equals B is false, but A equals D is true. Because it's not that A and B have the same value, it's that A and D are now literally the same memory object. And so equals is working that correctly in that regard. See the difference? There are two references that are pointing to the same bit of memory. Okay, so now if we do it the other way, which is the preferred way of, it's sort of the way in which you probably are thinking of equality. If we take the two that are equivalent, A and B, but are different memory objects, and we want to say if A equals B, now we see that A equals B is true, because the equals method is how we give an object the ability or the power to decide whether or not something should be considered equivalent, not whether they're literally the same memory. So think about that. The Java syntax gives us double equals and can check for us whether two memory locations are the same. So that makes sense because Java has the ability to just check whether two memory locations are the same. But it provides us the equals method in order to put intent into the behavior of our objects. Because Java as a language or as a machine doesn't know whether two objects that we create should be created equal. That's something that we need to decide. That's something that we put into our code. And so we do that through the equals method that we write, whereas the double equal symbol is something that the virtual machine checks for us. And that's just memory, and that's just, a mechanical check in a lot of ways. So the last one to demonstrate is that we actually decided what it was going to be equal. A equals B is maybe not interesting because the instance variables are exactly the same. But if we compare B and C, we can see that the instance variables vary, but the ones that we wrote equals to check, the width and the height, are consistent. So if we come down here and finally do the exact same thing, but do it on A and C instead, and run that, now we see that A equals C is true as well, even though all that varies is the width and height, or all that matches is the width and height. Okay? Pretty important concept for doing our if statements. All right, so just to summarize, the reason why we use that is because what we're usually asking for equals is whether or not they're should be considered equals. Okay, it is 11:22. We're a little over halfway through. What I would like to do is just take a 5-minute stretch break, get some more water. We'll come back at 23. We'll come back at 28 and pick up with the next question or the next issue, which is about a generic comparison rather than equals. And then we have a bunch of exercises, interactive exercises to work on. Okay? All right, so back at 28. Okay, welcome back. So when we left, we were talking about equality on strings, and as a general rule of thumb, it's probably the case that when you're doing equals and you're working with objects, you probably want to use the equals method. You can use that on double objects, integer objects. So one of the reasons why this is maybe a little vague is because one of the things that we're doing in this version of the course is we're not talking about primitive variables. So lowercase d doubles, lowercase I integers, lowercase b booleans. Those are the ones that you traditionally would use the straightforward relational operators on. But anytime when you use the object versions of them, the ones that have the capital letters, it's better to use the equals method along the way to make sure you're not comparing the memory locations. You're comparing your intent with the objects, why you want it. So there's a slightly more robust way of checking equality, and that's the compare to method. The compare to method, the equals method, those are both implemented for you on common data types like string and double and integer. If you write your own classes, like you just saw me do with the rectangle class, you have to implement your own equals and your own compare to. But fortunately, Eclipse gives you a little bit of help. It'll write the equals for you if you use it. Compare to is a little different. What compare to does is it enables you to have a total ordering over all objects of a particular class, meaning not just checking whether or not they're equals, but putting them in line in some sort of greater, ascending order or descending order, depending on what you want. And again, just like equality, deciding which object comes before another object is really up to the programmer that implements that object. So what we can do is we can use a compare to method to tell whether one object should come first or another object should come first. And the way it works is we call the method compare to. And in the first example here, when we compare string 1 to string 2, if string 1 should come before string 2, then the result of that is going to be negative. If the result of that is positive, greater than 0, then string 2 should come first. And then finally, if it's equal to 0, then string 1 and string 2 are equivalent. So the sorting operations that are built into Eclipse built into Java, will automatically sort your objects for you if you have them in some sortable collection like a list. And the way it can tell whether one of your objects should come before another one of your objects is by using the compare to method. So if we wanted to do that, we could then say, well, how should we go about trying to compare two rectangles to one another? Well, it's up to us to determine what's the equivalent of two rectangles. How are two rectangles equal? Well, let's say that we wanted to put two rectangles in order according to the area of the rectangles. Well, then rectangle 1 compared to rectangle 2 should be less than 0 if rectangle 1's area is smaller. So let's go ahead and just implement that, and we can see how that would work out. So we've already done rectangle. So let's implement a compare to method. So we know that it should be less than 0 if this is smaller. In terms of what? So we have to decide that. And so what we'll say is if this.get area is less than other.get area, then we'll return -1 because the first one is smaller and so it should come first. We're returning at that moment, and so we're not, this should not be returning a Boolean, it should be returning an integer. Okay, if we didn't return from that, then we can just make an independent check, and we can say if this.get area is greater than that, we'll return a 1, that's greater than 0. And then finally, the only other case is that they're equivalent, so we can just return 0. So this is going to compare two objects together. It's, we can test them as well, of course. We can just come up here and ask ourselves what happens if we compare one to the other. And what I do wrong, I have to concatenate those two. So the fact that A and B are have the same area makes them compare to 0, or It makes the comparative function come to 0. If we compare A and C, we see that A and C are 0. And then if we compare B and C, I think they're all 0. They all have the same area. Now we have to be careful here because our sense of what equality is has shifted. Because our equality method originally said whether or not the width and the height were the same, like the width was equivalent, one rectangle's width was the same as the other rectangle's width, and one rectangle's height was the same as the other rectangle's height. But now with the compare-to method, we've changed that. Two rectangles their compare-to can be 0, meaning they're equal, but now our standard is whether or not the area is the same, not whether or not the widths are literally the same and the height are literally the same. And what I mean by that is we can come up here and we can say that rectangle, let's make rectangle E, and rectangle E can be at 0, 0, and it can have, so we see that the area of this is 200. So we could have a rectangle that was 2 on a side and 100 on the height. And if we come down here and compare A and E, then they're going to compare to 0, which is our interpretation of being equivalent, but it's a different way of doing equivalence. And so what that just speaks to is that usually when you implement equals and compare to, you want to make sure that the sense of equality is the same. They don't have to be, but you have to just be aware of that. Make sense what's going on? Compare to is used by the sorting mechanisms built into Eclipse in order to put things into order if we wanted to sort an array of these things. So here's the question. What I would like to pause and give you guys a chance to do is try to explore lexicographic ordering. So in Java, two strings can be compared to one another, but it's not clear in certain cases whether strings should come before one another or not. Languages each handle this in different ways. So what I would like you guys to do is take a few minutes, and for folks at home, take a few minutes, and let's see if we can come up with what the rules are in Java for comparing two strings. So things that we might want to consider is we might want to consider if we had two words like cat and catalog, where cat is a smaller version of the characters in catalog, which one comes first? We might want to ask, does cat with a lowercase c and a capital C, how do those relate to cat and catalog? And lastly, how do international characters reflect our understanding of lexicographic ordering? So in order to do this, what you'll need to do is you'll need to make a new class that has a main method, make some string literals, string A equals whatever you want to test, string B equals whatever you want to test. And we'll take, actually maybe we'll take about 10 minutes to do this. And then you guys try and solidify what the rules are. And we're not going to be able to figure out, each individual person isn't going to be able to figure out what all the rules are, but maybe you can identify some specific rules by making some test cases. So that makes sense? All right. So let's come back at 39, let's come back at 48, and we'll talk about what rules we were able to figure out by writing the code ourselves. All right, stand by. See you at 48. Okay, welcome back. We had a good investigation about which strings come before which other strings, and so because there are so many different kinds of characters that we can represent within a string, we don't say alphabetic ordering because there are characters that are not part of the alphabet. There are characters that are not part of the English alphabet, and so instead we use the term lexicographic ordering, which just reflects the fact that we're dealing with all kinds of different characters. So we ran through a bunch of different examples in class here, and we proved that capital letters come first. So we did an example of CAT with a capital C and CAT with a lowercase c, and the capital CAT came first. We also saw, not surprisingly, that alphabetic ordering in the English language is respected. So lowercase a comes before lowercase b. We saw that punctuation is ordered. It wasn't clear exactly what the ordering of punctuation is, but we did see that an exclamation mark came before an equal sign. So there is an ordering to punctuation, even though we don't maybe know what it is. We looked at some internationalization. So we saw that English characters come before Arabic characters, for example. We saw that English characters come before Chinese characters. And we also discovered that Arabic characters come before Chinese characters. I can talk about that in a second. We discovered that lexicographic ordering means that short words come before longer words. So all the other things being equal, if you have two strings and one is a prefix of the other, the prefix is going to come first. We also saw that when we have digits, numerical digits that are represented as characters rather than the numbers themselves, those digits are going to come before letters in the string. So part of the historical trajectory for why it is the way it is, like why should it be that all English characters come before all other international characters? That's sort of an interesting quirk of programming languages, that English is elevated above all the other languages. Well, that's because it wasn't until about like the late 80s or early 90s when computers realized there were other languages in the world. And up to that point, the only languages that could be represented were English, and languages that just used English characters. There was a character encoding called ASCII, ASCII. It still stands for the American Standard for Character Something Information Interchange, I think. And what that was is that was 128 different, it used 128 numbers in order to represent 128 different characters. So that included the lowercase letters, the uppercase letters, the digits, the punctuations, and some control characters like space and backspace and delete. And those 127 characters were all that were possible to type in on computers for a long time. Then sometime, the timing is off, but I'm going to say sometime, at least in my awareness, sometime in the early 90s, mid-90s, there was a push to switch from ASCII as the way in which characters were encoded into a more international character set called Unicode. And Unicode enabled all the different glyphs from all the different languages to be incorporated into strings. And so the first thing that happened is we saw characters that were kind of like English characters get incorporated, things like the ennyes and the umlauts and accented characters. And then after that, characters that were completely stroked completely differently, like Arabic characters or Chinese characters or other Asian language characters, Sanskrit, things like that were incorporated. And then finally, there are some historical languages that were incorporated, like hieroglyphics, one of my favorites, Sanskrit, and off the top of my head, I can't think of any others. What's that? Emoji, yeah, emoji is probably the most recent addition. They're also represented in Unicode. They're in a special location in Unicode, and they have kind of this halfway status. They're not in a section of the code bank that are considered letters. They're sort of in this. It's like when we talk about a broadband spectrum, how there's some broadband that's regulated and there's some that's freeform, and so some kinds of RF spectrum exist in this free area. Emoji are kind of like that. Emoji are sort of pseudo-standardized, and so one thing that you'll see is that if you put like a coffee cup emoji into your text message, if someone has a different operating system on their phone, the actual image looks different. Right, you'll have a coffee cup in one and a different looking coffee cup, or a squid. I know a squid shows up really different, or the octopus shows up different systems. And that's because emoji aren't really standardized. They're not standardized like a letter A is, where you have different fonts that draw A's exactly the same way. I guess you could kind of have different emoji fonts if you wanted to.
Yeah.
Where a particular, what's that?
Samsung emoji font, Google emoji
Yeah, there's no reason why you couldn't do that. And that couldn't be treated exactly like fonts for the letter A, but it's just not. So, for example, when you try and write code, you can use Unicode international characters in your variable names in Java. So you could write your variable names in Arabic if you wanted to. Good luck on trying to get your forward and backwards correctly.
Could you write them in emojis?
You can't write them in emojis. You can put emojis in strings, but you can't use emojis in your variable names. At least the last time I checked this about 6 months ago. It's always changing. So that just reflects the fact that emojis are in this like hinterland of characters that are sort of pseudo-regulated. Nonetheless, in less than six weeks, in less than 4 weeks, we're going to have a whole new set of emoji that I'm very excited about, including the microbe. I'm really excited about the microbe. Yeah. Okay, so that all reflects the fact that strings have a particular understanding of ordering, and that is encoded in the Compareto method. Compareto method is going to reflect the results that we figured out. For English words, for the most part, it is exactly what we expect. As long as capitalization is the same, things are alphabetic. But you quickly get into situations where the characters aren't English characters. Okay, we looked at the double equals operator. I had this slide in place if we didn't actually end up checking that beforehand, but we saw that the double equals operator is not checking whether two things are equivalent. They're checking whether or not they're exactly the same memory spots. It's also worth pointing out that we can test for null as well. Null isn't something that we've worked with very often, but null is what happens when you have a reference and you haven't actually assigned it to something yet. And you can set them manually to null if you want to, but you can also check for it. So I'll just demonstrate that real quick here in Eclipse. A right now is a rectangle class, but we could say A equals null, and that's the equivalent of saying that whatever memory A was pointing to, A is no longer pointing to that memory, and now A is pointing to nothing. And if we tried to do something like, say, a.getArea, that would actually cause a null pointer exception. That would cause our program to crash. I'll demonstrate the crashing. You can see that we got through A compare B, A compare C, B compare C, A compare E. So far, so good. But when we got down to a.getArea, our program crashed. We had a null pointer exception. And what that means is that we tried to call a method which is in some memory that's reserved. Like, we can't call that method unless we've actually have memory and A is pointing to something that has that method implemented. When we set A equals to null, when we use that dot notation to try and go into that reference, there's nothing there. And so we got a null pointer exception. So if you ever get a null pointer exception, what you should look for is you should look for that dot notation and realize that what's on the left of the dot probably doesn't have an object assigned to it. To prevent that, you can do something like this. If you aren't sure whether or not it's null, you can ask whether A is null, and then, or I guess more to the point, you'd ask if it's not equal to null. And if it's not equal to null, then you can go ahead and call that method. Now, Eclipse is telling me that that's impossible because you just set A equal to null, so that's never going to get run. Dead code is the way it explains that. But if we left this empty, you could do it that way. Let's see, there was something I was going to say about that. I just lost my train of reference. Let's see. Train of reference left the station. If A is not equal to null, A.getArea. Yeah, I guess that's it. Okay, fine. Everything's good. All right, so let's just make sure we understand this. Walk through me. What's the difference between these 4 different lines? What do you think?
The third one is wrong.
Okay, what's wrong with the third one?
It just looks.
It makes me uncomfortable.
Yeah. It makes me uncomfortable.
Makes you uncomfortable because we haven't seen triple equals?
Yes.
Yeah. So in Java, there's no triple equals is not a thing. In JavaScript, triple equals is a thing, but in Java, it's not a thing. But Java and JavaScript are not the same. Radically different. Don't let anyone tell you anything differently.
Someone told me that JavaScript was better than Java.
That's foolish talk. Yeah, that's nonsense. That's crazy. I can't believe anyone would even assert that. All right, so third one's bad. Get that. What's the first one doing?
It's setting box 2 equal to box 1.
Other way around.
Box 1 equal to box 2.
And so at the end of that, we know that box 1 and box 2, assuming they're references to a box, if box 1 and box 2 are actually going to be pointing at the same memory location. So what's the second one checking?
To make sure
pointing the same memory, right? And if we ran the first one, then the second one. If we ran the first one right before we ran the second one would be true. So what's the fourth one doing? Right. We should consider them equivalent according to whatever standard we wanted to use. Or perhaps in the case of string, for example, equals has already been decided for us. But if we were implementing whatever whatever type box one is, we would implement that. Great. Okay, so just a few if-else examples. These are drawn from the book. So this is just to emphasize the point that the order in which you ask these questions matter. So this is an example of trying to evaluate the effect of an earthquake. And the idea is that we have a variable called Richter, and it is a sensor that is measuring the strength of an earthquake. And before we run this code, it's going to be set to the power of the earthquake that we just recently, that this code is testing. And so what we can see here is that we're going through this if-else example, and we're asking if the Richter scale was greater than or equal to 8, then what we want the description that we're going to use later to be is that most structures fail. If it was greater than or equal to 8, we'll jump out of that first clause and immediately go to the very bottom of this. We'll run no other code on this slide. But if it's less than 8, then we'll check the second test. If it's greater than or equal to 7, if it's greater than or equal to 6, greater than or equal to 4.5, and if it's anything less than 4.5, we'll get a description that says no destruction of buildings, including if it's negative. And I don't think a negative Richter scale number is a thing. But what I just want to drive home this point that the order in which you ask those questions in the if-else statements matter. Because here's an example where we test in the wrong order. So if we were to order these in the opposite order, where first we checked greater than or equal to 4.5, and then 6, and then 7, and then 8, this would be a logic error. Because let's say, for example, that our Richter scale variable was set to 8. We would go to that first clause. If Richter is greater than or equal to 4, we'd evaluate to true, and we would run no other clauses. But that wasn't our intent. Our intent was that if Richter was very high, we would want description set equal to most structures fall. But what would actually happen is we would get a description of damage to poorly constructed buildings. That's because that first if clause captured everything greater than 4.5, and we never got the chance to execute the ones below it. In fact, in this code, the 3 clauses that fall after that first one are never going to get executed. There's no way that control flow can go through this code and execute any of those third statements, because the first one is capturing all possible situations where Richter is greater than 4.5 or equal. So the last one that we can look at is we can look at one in which the independence of these different statements is not linked. There's no else's here. And so because of that, we have four different if statements that are all going to be evaluated no matter what. And so if the Richter scale value, the variable Richter, is greater than 8, well, yeah, it's going to work in the first one. Our description is going to end up being most structures fall. But because it's an independent if statement that follows it, it will then get overwritten with most buildings destroyed. And then if Richter is 8, it'll get overwritten again with many buildings considerably damaged, some collapse. And then if it's 8, it'll get overwritten again. Oh, sorry, there's a bug there. That last one should be description equals damage to poorly constructed buildings. It would get overwritten again. So that if Richter is greater than 8, after we pass through this code, we would not get the message that we wanted because we forgot to put else statements in there. If we had put else's in front of the 1, 2, 3 different ifs after that, we would have almost gotten the correct answer. And the reason why we wouldn't have gotten the perfect answer is because we don't have an else statement down here at the end, like a default else statement. Okay, so let's see. Let's make sure that we understand this syntax. Let's see. How are we doing on time? We have about 10 more minutes. I've got 3 more examples. But what I would like to do is I would like to not do these 2 examples. I'd like to do our final example. So let me just talk through this one really quickly. If you would like to do this on your own as a way of testing your knowledge of the if statements, what this exercise is asking you to do is take each one of those A, B, C, and D examples as 4 different problems and take 10 as the input that the user would type in. So that first line up there, int hour equals in.nextInt, is a way of getting input in from the user through the console. And so I'm asking you, if hour were set equal to 10, in case A, what would time be set equal to? And the same with if hour was set to 12 and 2 and 22. So 4 different runs of this code. What you should be able to do is take that input and understand which lines of code are going to get run and what time is going to be at the end of it. Now, this particular code may or may not work. Here's another example. This code has been changed, and there's some different questions here. And so trying to understand the control flow there is the goal. Let's let those go, and you can return to them if you would like to double-check your understanding of if-else statements. The last thing that I want to work with you on is Boolean variables and their operators. We didn't explicitly introduce Boolean operators, but Boolean operators are variables that are either true or false. And so there are 2 new relational operators that get introduced in this situation. I'm going to introduce them in code, and then we can work with them for a moment. So we'll come down to the bottom of this code here and create a new little chunk of code. So to introduce a Boolean variable, you use capital B, O-L-E, and a variable name, for example, joy. And we can say that we can do it a couple ways. We can say that that equals true or false. We can say it equals true. We can say that the variable equals true or false. That's all they can equal. We can also use a constructor and say that it equals a new Boolean, and we can explicitly pass that into the constructor. So that's another option as well. So that's 4 different ways of initializing a variable. But the other thing that we can do is we can set it equal to the result of a relational operator. So we can, for example, say A dot equals B. So it's as if we are running the relational operator in our if statement and storing the result in that variable joy. And then we can do an if statement based on it. So we could just say if joy, then we'll just put a comment here. Then A equals B. Oh, sorry. So Booleans can be true or false. Now, the 2 additional operators that we have available to us are we have an operator and 2 ampersands and 2 vertical bars. And the ampersand stands for logical and, like that, and the vertical bars are logical or. And the way this gets evaluated is if true and true, then that's going to get executed. True and false is not executed. False and true is not executed. And false is not executed. So this is a truth table for the AND function. So why would you want to do this? Well, you might want to only do something if 2 conditions are both true at the same time. All right, so let's say that we have a Boolean variable. It has stored the result of some computation we want to do. And if we come down here lower, we can say, well, maybe let's create 2. So we've got Joy, and let's who's next on the line? Lisa. So later on down here in the code, we can say if Joy and Lisa. So what that means is if Joy is true and Lisa is true, then we're going to execute this. It's just a relational operator. We can do it that way if we want. Now the other relational operator is the OR function. So we can say if true or true, then this is executed. And it's a little bit different than AND, because if we say false or true, that's also executed. And if we say true and false, that's executed. So the order doesn't matter. The only time it's not executed is if it's false and false, false or false. So then if we say if Joy or Lisa, then something happens. So in this case, we don't want to check if both of them are true. We want to check if either one of them is true. And these are just helpful sometimes if we've got complicated statements. Like if you want to check, for example, if water is a liquid, you might ask if the temperature is less than 0 if the temperature is greater than 0 and the temperature is less than 100. So it's not frozen and it's not a gas. You might want to put those two things together. So that would look like if temperature is greater than 0, and I want to put some extra parentheses in there, and temperature is less than 100, we have water. Okay, so that would come out true. Okay, so the last thing that I would like to do, and you know what, let me introduce it actually, and then what we'll do is we'll do it at the beginning of next class because we're sort of running out of time to do it well. I want to do a code trace example here. So the idea here is that you are maybe a robotic car or you're an Uber driver, and you're starting at Westmont. That's the circle in the upper right there. And there are 4 different intersections that you're going to come to, A, B, C, and D. And that's going to put you at possibly 5 different locations: Hale Park, Parma Park, Franceschi Park, Alameda Park, or Chase Palm Park. And what I'd like you to do, or what we'll do at the beginning of next class, is that we'll take those 4 Boolean variables, write at A, write at B, write at C, write at D, and assume that they have been set correctly. So we're driving from Westmont College. And the goal is to have an if statement that writes out the name of the park that you're currently at, regardless of whether write A, write B, write C, or write D are true or false, but assuming that they've been set correctly. Okay. So we'll start next class on that thought. All right, so just to wrap up today, we continued looking at the decision statements. I thought there's a lot of details that we had to cover that I wasn't expecting actually to cover. Actually, I had forgotten that we needed to cover them. So we didn't get into loops quite as fast as we intended to. We looked at the if statements. We looked at the equals, the double equals and compare to. We looked at relational operators. Those are all really important aspects of comparing things together. What else did we do? We looked at how strings are ordered lexicographically. We did some exercises about equality. We looked at how you would implement an equals method and a compare to method in the rectangle class. At the very beginning, we just looked at the mapping between an if statement and the flowchart that we introduced if-else statements with. Next class, what we'll do is we'll continue with this exercise. We'll pick up starting to talk about loops. And one of the things I'd like to do in next class is to introduce JMonkey Engine, which is the 3D graphical environment. It's more of a game environment or kind of Minecraft sort of environment. And we'll use that to draw some of our boxes and use that to execute some of our loops. Any questions before we wrap up for today? Logistic or otherwise? Comments? Okay, we're done. Thank you for your attention.